Alright, in this video we're going to be looking at how we can use implicit differentiation when finding horizontal and vertical tangent lines. So basically this is something that we've seen before in the video about horizontal and vertical tangent lines, but just in the scenario where what we're differentiating is an implicit equation. So just as a quick recap, when we're looking at horizontal and vertical tangent lines, let's see what we're dealing with here. So let's draw that line a bit straighter. But basically, with horizontal and vertical tangent lines, a horizontal tangent line exists when the slope is 0. So a horizontal, this is called HTL, horizontal tangent line, exists when dy dx is 0. And now, a vertical tangent line exists when, I'm just using this so I don't have to write the word again, exists when dy dx is undefined. The reason just lies in the basic fact that a horizontal tangent line is a horizontal line. It's not horizontal. A horizontal line, and a horizontal line has a slope of 0. Vertical lines are just literally straight lines that go from up to down, right? And straight lines, as we should know by now, have no slope. Their slope is undefined. So obviously, if we want to find a vertical tangent line, that's when dy dx is undefined, and horizontal tangent line is when dy dx is 0. All right, so now if we're given the equation for an implicit equation, right, describing some graph, and we want to find all the tangent lines of that graph, let's say we're given some function 4x squared, 4x squared plus 3y squared is equal to 16. How would we go about finding the horizontal tangent lines and then the vertical tangent lines? How do you do that? So let's start with horizontal tangent lines. If you remember what I said like 30 seconds ago, a horizontal tangent line is present when the slope is equal to 0. So what we have to do then is we'll have to find the slope, the expression for the derivative of this function, or the derivative of this equation here, set it equal to 0, or basically figure out when that derivative is equal to 0. So this is an implicit function, clearly, so let's use implicit differentiation to find its derivative. So this would become 8x plus 6y dy dx equals 0. We then can isolate for dy dx, right? To do that, we then just get dy dx is equal to, we bring it over, we get excuse me, we get minus 8x divided by 6y. So now that we get this, again, we can simplify this a bit, and we just get minus 4 over 3, so minus 4x over 3y. So this is, and this is our derivative here. This is the derivative. So now, in order to find the horizontal tangent line, we have to see when this derivative would be equal to 0. So when is this derivative equal to 0? It's equal to 0. Well, 1 if the numerator is equal to 0. When is the numerator equal to 0? Let's set it equal to 0 and find out. Minus 4x is equal to 0 when x is equal to 0. Okay, so now we know that y can't be equal to 0 because if we set y to equal to 0, we can't have 0 in the denominator, right? That would be undefined. Kind of a hint at how we're looking for the next step for vertical tangent lines, but staying on course here, we know that this line or this derivative would equal to 0 when our x is equal to 0. So then how do we figure out the y, right? The y. We know the x. So to figure out the y, we just plug that into our equation here. So we get 4 times 0 squared plus 3y squared is equal to 16. This is 0, so we then get 3y squared is equal to 16. Y is equal to 16 divided by 3, square root of that, right? So plus or minus. So the horizontal tangent line is when y is equal to plus or minus the square root of 16 thirds. All right. And again, we know that a horizontal line is in the form y equals something. So y equals, in this case, plus or minus the square root of 16 thirds. That is the equation of this tangent line. Specifically, this horizontal tangent line. All right. Now, when we're trying to find the... Actually, let's not get rid of all of that work. When we're trying to find the vertical tangent line now, let's hold on to our original derivative here. I guess I erased that already, but we can basically take the derivative, right? If we take the derivative of this expression as we did earlier, we end up with minus 4x over 3y, I believe. This was equal to our dy dx. So this is our slope. For a vertical tangent line, we have to see when this is undefined. I kind of gave away the answer earlier, but we know that this is undefined when the denominator is equal to 0. So we have to set the denominator equal to 0. 3y is equal to 0. Get that y is equal to 0. So 3y equals 0 when y is 0. So this function, or this derivative, is undefined when y is equal to 0. But we're trying to find a vertical tangent line. A vertical tangent line is in the form x equals something, right? So if we want to do that, that means we have to figure out the x value. This is the exact same approach that we used earlier. So now, in this case, we get 4x squared is equal to 3 times 0 squared is equal to 16. 4x squared is equal to 16. X is equal to 16 divided by 4 is 4. Square root of 4 is equal to plus or minus 2. So this is then going to be our answer here. Our answer here is plus or minus 2. This is the equation for our vertical tangent line. So that's really all I wanted to demonstrate in this video, how we can use implicit differentiation in finding horizontal and vertical tangent lines. Just keep in mind the common area where students mess up is they plug that value, right? We solved for, when we were doing this last step here, we saw that we had to see when our derivative would equal 0, for example. So in order to do this, we got what x value, at which x value this derivative would be 0. Students often plug this back into the derivative, but that is incorrect. Remember, or be conscious of what each expression is representing. Remember, if we want to find a y value given an x value, we plug it into the... Again, this is not a function, but just for simplicity, let's say we plug it into the function, right? We plug in an x value, we get the y value. If we plug in the x value into our equation, we will get the y value. So we have to make sure we plug it into the correct equation, which is the original equation, not the derivative equation. The derivative gives you a slope. The original equation gives you a y value or an x value when you plug it in. So make sure that you're plugging this back into the original equation. I've seen way too many students lose points because they end up plugging it into the wrong equation. They were doing everything else right and getting the wrong answer. So make sure you do not do that. But other than that, that brings us to the end of this video. So hopefully you found it useful. If you did, please show your support by liking, subscribing, and leave in the comments any questions you may have or what you'd like to see for future videos. And I will see you in the next one.